All right, this is section 11.5. This is on lines in space. Let's be more specific, lines in 3D space. So what we want to talk about here is a few ways of describing lines formulaically in a manner that's useful. We're not really going to be talking about sketching them. We won't actually sketch a lot of lines in three-dimensional space, at least. In two-dimensional space a little bit, but then they're much easier. So worry less about sketching them. We'll do a couple of easy ones than about understanding the formulas that we need. So for an intro, we can say, there'll be a few different ways. So we can say some ways of describing lines. In, let's say, 3D and 2D space. So there are a few ways to do this, and I'm taking a slightly different approach from the book in terms of introducing them. So when we think about describing a line, we could say, for example, that 2 points make a line. But actually, let's do this. Let's do a brief review. So in 2D, like in pre-calc, right, we could, for example, say that 2 points give a line. So 2 points yield a line. All right, like if you have an XY plane, and you take a point, you take another point, you know for sure that you'll get a line that goes between them. But knowing those 2 points isn't as relevant as finding an equation for the line, right? So the goal here, back in pre-calc, would be to get something like y equals mx plus b. And the reason for this is that this thing is insanely useful. Right? It's an equation, you can work with it, you can plug things in, etc. So knowing 2 points, it's fine, but the goal is invariably to get the equation, and the equation is more useful. So the idea here is the same. Is to say, like, what's useful? What is a useful way to describe a line? And we'll say in 3D for now. So what we'll do is we'll start by looking at sort of like a similar thing to 2 points. I'm not going to take 2 points and make a line, though. I'm going to take a different approach. So at the end of the day, however, there will be 3 ways. And the first one of those, I'm going to call these the parametric form. Don't worry about where this term comes from right now. That's not a problem. What I want you to do instead is think about different ways we could describe a line. So one way would be 2 points, for example. Another way in three-dimensional space is we could describe a line just off the cuff using a point and a vector. Right? So in other words, suppose we have a point P. So P will be, say, x0, y0, and z0, and a vector L. So L will be the vector, say, AI plus BJ plus CK. So together, in three-dimensional space, these sort of describe a line. And so you want to picture the following in three-dimensional space. So picture that you have a point right here floating in three-dimensional space. That's our P. And then picture we have a vector. And let's make the vector pink, for example. And we're going to attach the vector, since we can attach it anywhere. I'm going to attach it here. That's L. So picture this in 3 dimensions. You can sort of imagine that you have a point floating in space and a vector that's attached to it. So from here, we automatically get a line, and we can see that this line would be this line. And this goes on forever and ever and ever and ever and ever in both directions. So P and L together form a line, at least visually. Now, we don't yet have an equation, right? Or we have a sort of an understanding that there's a line made up. But we could ask the following question. We could say, what other points are on the line, right? So we know that P is on the line. Right, that's not a question, it's a statement. What other points? So you could say, well, look, if I take P and I add L to it, right? That's a bit weird. I'm adding a vector to a point, but just roll with it. If I add L to it, I get a new point on the line, right? We could say, well, P plus L or P minus L. I'll draw all these in a second. Or P plus 1/2 L or P plus 3L dot, 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 right? So to understand what we're saying here, take our P. We will say, let me just do this. Let me draw the vector L again. Let me draw the entire line again. And then I'm going to mark off some of these points. So for example, P plus L, we can think about this as this point right here. P minus L would be back here in the opposite direction. P plus 1/2 L would be right here. P plus 3L would be way out here, 3 vectors along. So what we start to see is, we see that I could take P and I could add any multiple of L. We can take P and add, let's say, any multiple of L to get a new point on the line, or to get, let's say, all the points on the line. So how does this work in practice, right? Like if I gave you a P and an L, how would I find some other points on the line? Right? So this question is, how does this work in practice? So let me clear the left-hand side of the screen off, and we'll do an example and introduce some new terminology and just sort of get this parametric form. Let's look at an example. And this example will help us write down a final definition. Suppose a line L, or suppose a line has point, say, 3, 2, 5, and direction. So this vector L is called the direction vector. And L will be, which just sort of indicates which way it goes. Say, 1I plus 4J minus 2K. So we could then say, okay, what are some other points on the line? So according to our little calculation, or a little observation on the right-hand side, I can take the point P, this is our P right here, and I can add L, subtract L. So here are some. We could do, say, 3, 2, 5 plus L. Now, again, I'm being really, really informal here. Right, in the sense that I'm adding a point to a vector. I don't want to do this formally, right? I'm just sort of doing this informally to help us see what's going on. But I'm taking the point and I'm sort of looking at the point that's at the end of the vector. So this would be, say, 4, 6, and 5 minus 2 is 3. That's another point. Or I could subtract it. I get 3 minus 1 is 2. I get 2 minus 4 is negative 2. And 5 minus a minus 2 is 7. But again, this is informal. So we could do instead, we could do something. We could write it, for example, like just 3 plus 1, 2 plus 4, 5 minus 2, etc. Or 3 minus 1, 2 minus 4. I'm doing the exact same calculations here. 5 minus a minus 2. That'd be 2, negative 2, 7. But we start to see what's happening here. Right, what's happening is we're getting the following points. We're getting, let's say it this way, all points of the form. So remember how this works, right? Let me just point something out here. Back at the beginning of the problem. This P right here, this was our x0, y0, z0. And this L right here, this was our AI plus BJ plus CK. So what we're doing is we're getting a bunch of new points. We're getting points of the form x0 plus some multiple of A. So let's say AT. We're getting y0 plus that same multiple of B. And we're getting z0 plus that same multiple of t. So for example, when t is 1, we're adding the vector. When t is 2, we're adding twice the vector. When t is negative 1, we're subtracting the vector. This set of points, this is the parametric form of the line. Or let's say the parametric equations of the line. And again, the point is that each t value corresponds to a point on the line. So let me do two examples. I want to do one that's kind of like the one we just did, and one that's there's a little more thinking involved. So let me clear the right-hand side of the screen off. So for example, if we said find the parametric equations of the line with point, say 4, 0, 3, and direction, say L equals 2I plus 7J minus 5K. The solution to this, we would take our initial point 4, the x, and we would add 2t. That 2 comes from the L. We would take y as 0 plus 7t, and z is 3 minus 5t. And again, each t gives a point on the line. Each point on the line comes from a t. So each t corresponds to a point on the line. So if I were to ask you some other points on the line, you would just plug in some t's, right? So for example, when t equals 1, I get 4 plus 2, 6, 0 plus 7, 7, 3 minus 5, negative 2. I get a new point on the line. But any t will do the job. Any t will work. Right? Now, I'll do one example, but before I do one more example, before I do the example and make a note here, is in order to do this, of course, I need to know L, right? So the key is that you need to know both a point and L. So for example, if L is not given, we must find it. So for example, if we said find the parametric equations of the line. Let's go back to basics and say connecting 2 points. Say 1, 4, 3, and 2, 5, 10. So notice we've got a point. We've got 2 points, in fact. We have 2 points and no L. Well, let's say 2 points, but no L. What can we do? So the answer is that we need to find L. And so I'm going to draw a picture here. I'm not going to draw these exact points because I have to plot those in 3 dimensions. It's pretty awkward. But I want to draw 2 points to give us an idea of what's going on. Because again, we need to find the L. So look at the following. Suppose you have 2 points. Let's say P and Q. And you are interested in this line that connects them. You say, look, what direction does it go? Well, the obvious thing to do is to take this vector that connects them. So here's the key, is that for L, for our L, we can use PQ. Remember this notation? This is the vector that goes from P to Q. Now you might say, could I use QP? Goes in the other direction. The answer is absolutely, there are options here. So the key is, though, to use a vector that connects the point, right? So for our example, so for our problem, if we say that P is the first one and Q is the second one, then our L will be PQ. Goes in the direction of the line. Remember how PQ is done? I take Q and I subtract P. Remember this was done basically by doing that kind of a thing. So I get the vector 2 minus 1, 1i, 5 minus 4, 10 minus 3. So then we take P and L. So remember how this works. I take P, that's the 1 from the P, plus 1t. That's from the L. Y is 4 plus 1t. Z is 3 plus 7t. And again, if you're a bit confused, this can be confusing early on when you're still finding out where all these things come from. These guys, these are our x0, y0, z0. Those come from P, right there. And these coefficients, I'll put a box around, I don't want to mess up the picture too much. Those come from the L. They come from right there. So those together, those 3, let me rewrite them so they're not all cluttered. You don't need like the 1t, you could just put a t, of course. I'm just putting it there so that you can really see. That is our final answer. That's the parametric equations of that line. Now, something to notice, we used P for our point. You could have used Q. We used PQ. You could have used QP. So you might get a different looking answer. So if you use QP instead of PQ, the answer may look different, or would look different. That's okay. In other words, the parametric equations are not unique. You may get things that look different than something that somebody else did, or that the solutions manual says, but they will be the same line. So this seems like it took a while just to get one of the 3 kinds down, because I said there would be 3 different kinds of equations, but getting this one down is the hardest part. Once we've got this one down, looking at the other 2 will be easy, right? So the next one I want to look at is what's called the vector equation of the line. The vector equation of a line is easy if you know the parametric equation of the line. So let me clear off the right-hand side of the screen, write down the parametric equations again, and then write down the vector equations. This is B, we'll call this the vector equation of a line. So like I said, this is really easy. So just to recall the parametric equations, it's worth rewriting these because these will play into both of the next two ways. Oops, it's a BT, not a CT. These are the parametric equations. So for the vector equation, all we're going to do is I'm going to put these into a vector. I'm going to write this. The tradition is to write it as R of t. There's no reason to worry right now about why that is. We'll see a little later on. So I'm literally, all I'm doing is I'm taking these three and I'm putting them in a vector. And that's it, right? Now, this is interestingly, this form of a line, we will not use that much first. And then later on in the book, this will become the de facto way that we'll do lines, right? This will be the way to do it, right? So it's worth mentioning right now, the reason for doing this is so that it's all in one compact formula, right? Like when we have the parametric equation, there are three different equations, and that's a bit unwieldy. You sort of have to carry all three of them around. So the reason for having them like this is nice and compact. And later on, when we start talking about motion of objects, things like that, this will be the way to do it. So for right now, don't worry so much. Like, don't get overly concerned about the fact that it's a vector. It seems a bit weird, but it's describing a line. Just think like, all right, put these things together in a vector. And so, for example, the previous example over here on the left, this would simply be R of t is 1 plus 1 ti plus 4 plus 1 tj plus 3 plus 7 tk. And now, in this case, just so that we're clear, each t gives a vector which points from the origin to a point on the line. So, for example, if you did r of, say, 2, right, this is 3i plus 6j. I'm just plugging a 2 into the r of t plus 17k. What we're really doing with this is this points from the origin to the point 3, 6, 17, which is on the line. So again, if it seems a bit weird that we're using a vector to represent a point on the line, that's okay for right now. Just put it aside. It's just something that we'll use a lot later. For now, it's just something to remember. So the last one we're going to look is what are called the symmetric equations of the line. So let me leave the right-hand side because I want to use it still. I want to use the parametric equations again. Let me clear off the left-hand side. So this is C, this is the symmetric equations of a line. So the term symmetric here, just something to keep in mind, it comes from a deep mathematical idea, which is not something we're talking about. But when you hear the word symmetric and you think of like a mirror image or some kind of side-by-side symmetry or something like that, that isn't really where the term comes from. So don't worry overly much about where the term symmetric comes from in this case. So the observation I want you to make before I explain this is if we look back over on the right at the parametric equations and the vector equation, both of these involve this t, which can be a bit awkward, right? Like Why does the equation of the line have a t in it? What does this t represent? Things like that. So basically the symmetric equation is a way of rewriting this to get rid of the t, right? And so it's pretty easy to do. There are some special cases. Those are also pretty easy. But let me show you what the basic case is, right? So the basic idea is to take the parametric equations over here on the right, solve each of them for t, and then set them equal. Okay? So we take the parametric equations, solve each for t, and then we set them equal. Okay? So the first one, let's do this all really carefully. This one, if you solve for t, you would subtract x0 and you would divide by a. For this one, you would subtract y0 and divide by b. For the last one, you would subtract z0 and divide by c. Then you would set these equal because they're all t. And it's a really kind of funky equation here because the equation is like a double equation. This right here, this is the symmetric equation. Now, the useful thing about this is there's no t in it. It's useful because if you want to test if a point is on the line, you just plug the point in, you check that all the equations are the same. So I'll give you an example. So the symmetric equation of the line with point, say 1, 2, 3, and direction, say 4i plus 5j plus 6k. I picked the easy numbers so they're easy to see how they fit in, is simply the equation x minus 1 over 4 equals y minus 2 over 5 equals z minus 3 over 6. So then, for example, if we were to say, is the origin on the line? Right? So I'll just tuck this in here because it's really easy to see. Is 0, 0, 0 on this line? The answer is to plug it in. Is 0 minus 1 over 4 equal to 0 minus 2 over 5 equal to 0 minus 3 over 6? Right? The answer is no, right? Because negative 1/4 is not the same as negative 2/5, which is not the same as negative 3/6. So the answer is no. So really, really nice and easy, right? So the symmetric equation is useful in that regard. There's no additional variable in it. Now, I just want to mention the special cases really quickly. If you look at these, you may notice back in this equation right here, you might say to yourself, well, what if A or B or C were 0? Then you can't divide by it, right? And remember where A and B and C came from. Those come from the direction, right, of the line, the direction vector. So some of them could be 0. Like they can't all be 0 because the line has to have direction, right? One of them at least must be non-zero. But A could be 0 just by itself, so then you couldn't divide by it. Or A and C could be 0, so you couldn't divide by them. So there's this looming question of like, well, what do you do in the special cases? So the special cases are really, really easy. So let me just work through those. I'll just do one because there are 2 special cases. So I'll do an example of each. So let's say special case. Let's say, what if one of A, B, and C is 0? Just one of them, right? So the easiest way to do this is to go back to the parametric equations, right? So for example, suppose the point is negative 2, 4, 3. And let's say for the sake of argument that b is 0. So what you get is you get a vector that looks like maybe 5i plus 0j plus 7k. So the problem right now is that this b is 0. Now, here's the thing. Don't even think about it. Just, first of all, write down the parametric equations. So remember, that's x. So you take the point and you add the vector times t. So for the x's, I had -2 plus 5t. Then I have 4 plus 0t. Now, you don't need the 0t, of course, but just for the sake of argument, keeping it nice and tidy, 3 plus 7t. So here's the deal. Remember what the process was. We solved each of these for t. So this first one becomes x plus 2 over 5. That's t. The second one, we cannot solve for t because there's no t's. The third one is z minus 3 over 7 equals t. So all we do is this. For a solution, you take the two that you can solve for t and you set those equal. And then you leave the other one separately. So the other one says y equals 4. That's it. Done. All right, the y equals 4 cannot be mixed in with the other two. Like, it just doesn't work. Right? There's no t. You can't solve for it. You don't solve for it. You leave it alone. Right? So that's the first special case. So let's look at the special case, the second special case, where two of those things are 0. So here's the second special case. And we'll say, what if 2 of ABCs are 0? So let's do an example. Let's say, for example, that say A and C are both 0. Suppose P is something like -243 again. That was perfectly good. And L is, say, 0i plus 3. Let's do a different number than 3 because we used that number already. 7j and 0k. So again, we notice that we've got these two guys. So same deal. Like, don't worry about it. Just first say to yourself, like, well, what are the parametric equations? Right, so personally, I think it's almost always easiest to go through the parametric equations, right? They're the ones that make sense, I think, fundamentally, and everything else springs off of those. So the parametric equations, we have x is -2 plus 0t, y is 4 plus 7t, and z is 3 plus 0t. So now, like, this first one, we cannot solve for t. This last one, we cannot solve for t. Now this middle one we can, although it's kind of goofy because you might say, like, well, I can solve it for t, but there's nothing to set it equal to. So here's the interesting thing. Right? But the t thing can be anything. Right? The t is it's the parameter, right? Way back at the beginning, what we said is we said that each t gives you a point, and each point comes from a t. So in this equation right here in the middle, let me put a little box around it. In this guy that's all by itself, since t could be anything, y can be anything, right? Because if you want to make y really big, you make t really big. If you want to make y really negative, you can always find a t. So since t could be anything, y could be anything, and it doesn't affect x and z. Right? So what we do is we say this, right? Since t can be anything, so can y. This doesn't affect x and z. So this is what we write for a solution. I'm going to say, well, look, x is -2. That's it. There's no, because if you look at the equation, x is -2, and we know that z is 3. And then what you can put is you could just put y equals anything. Now, here's the thing. I'm going to put that. You don't even really need to list that, because in mathematics, when you put equations, when you put down an equation is a restriction. So to write this, right, like this part right here isn't even necessary. You don't even need to list it. You can put it, right? If it helps you cognitively think about what's going on, by all means put it. But you could just put x equals -2, y equals 3, done, right? This is not necessary because by not saying anything, you're allowing y to be anything it needs to be. So be aware of that, right? So the reason I want to mention these two special cases is because they look quite different, especially this second special case looks quite different from the basic symmetric equation of a line. So that's the end of the three equations. Now, there's one last thing I want to do. I want to give you a formula. It's sort of an esoteric formula for the distance from a point to a line, but it's a good formula to derive because it pulls up a lot of things we've learned so far in the course. And I can do an example that uses the symmetric equation of a line that looks a bit unusual too. So it's a good formula to end on. So I'll work through the derivation. I don't expect you to memorize the derivation, of course, but it's a good one to understand to see what's going on. So let me clear the screen off, derive the formula, give you the formula at the end, and then work through an example. So we'll say this is number 4, I believe. This is distance, point to line. And so here's a picture of what we got, right? So suppose we have a line. We're going to give a line with the two fundamental things, with point P and vector L. And we also have, let's say, another point, Q, which is not on the line. And the question is, how far is Q from the line? Now, when we say how far, what we're saying is what's the shortest distance, right? Like you can't just take the distance from Q to P because that may not be the closest point, right? So in other words, what we've got going on is we've got the line here, we've got P, we've got L, which we can think of like this, and we've got this Q that's floating over here, somewhere off the line. What we want to know is we want to know the distance that's quickest, that's shortest. In other words, let me mark that in green. We want this distance. So we say to ourselves, well, okay, how do I figure this out, right? Well, what we can do on this picture is we can fill in a small triangle, right? What we'll do is we'll fill in this right triangle right here. And from that right triangle, we need the distance. That's the opposite side from theta, right? There's an angle theta in here. And so we know that the sine of theta is the opposite over the adjacent. So the sine of theta, right, the opposite is the distance. That's the thing we want. Over the adjacent, which is the distance from P to Q. Now, we can write that a couple of different ways. We can write it as like this, using the notation from the first section, or we can write it as the way that we'll write it, which is the length of the vector PQ. Right, that's the vector that points from P to Q. Right? Now, either which way we do it, we'll do the second way because the way we want. This tells us that the distance that we're looking for is the magnitude of PQ times the sine of theta. Now, this may kind of ring a bell because the sine of theta came up in the cross product. Right? So remember, from the cross product, we had this basic fact for A and B, just some random A and B. So, in our case, we don't have an A and a B. We have a P, Q, and an L. Right? Here, this is what we have. Now, all I'm doing is I'm writing PQ in place of A and L in place of B. And then what I'm going to do is I'm going to solve for the absolute value of PQ times sine theta. Oh, sorry, the length of PQ times sine theta. That's the distance, right? So this guy, all I'm going to do is I'm going to divide both sides by the magnitude of L. Right, that follows immediately from here. But that's the distance. The distance is then the magnitude of PQ cross L over the magnitude of L. So that is a formula for the distance from a point to a line, from Q to the line containing P with direction L. That's our formula. Oops, I'm going to write a formula. So let's do an example. Let me start it over here so we have enough room. Right? So suppose a line has symmetric equation. I'm going to make this a bit confusing looking. Let's say x minus 2 equals, say, 3 minus y equals z. Find the distance from, say, the point 1, 5, 6 to this line. Now, the reason this is a bit confusing is the symmetric equation, I purposefully made it a bit weird looking, right? So the thing to do to help, there are a few ways to do this, but one way that might be useful is to look at this thing and remember how this works, right? The symmetric equation arose because each of those was equal to t. So if I rewrite those, the first one, let's say solution, oops, right, is I'm going to take each of those three and set them equal to t. And so this is x equals t plus 2. And the second one is 3 minus y equals t. So what I'm doing here, just so we're clear, is I'm rewriting it so I know what the point and the vector are. So this is, I'm going to solve for y. This is y equals negative t plus 3. And z equals t. That's just this, right? So remember how the symmetric equation arose is that these three things, let me box them in, these three tell us our point and they tell us our vector. Right? These three things tell us that our p, remember that's, let's do this in this order. The L is the coefficient of the t. So 1i minus 1j plus 1k. The p in this case is the point. That's the 2, 3, 0. So having this information lets us figure things out, right? So this is, we have our p, we have our L, we know q. Q is our point, which is not on the line. So let's see what we've got, right? So PQ, this is the vector from P to Q, right? So remember how this works. This is basically Q minus P. Right? So 156 minus 230. So 1 minus 2 is negative 1. 5 minus 3 is 2. 6 minus 0 is 6. That's PQ. I need PQ cross L. So let me rewrite L. So PQ cross L. Remember how this works? We did this in the last section. I'm going to do this one more time. I'll write down the little determinants. So for PQ cross L, I hide the i's. I do 2, 6, negative 1, 1. Hide the j's. Hide the k's. So this is going to be, I'm going to try and make this fit in without erasing too much. This be 2 times 1 plus 6 is 8i. Negative 1 times 1 is negative 1. Minus 6 is negative 7, so it's plus 7j. And 1 minus 2 is negative 1k. So then the distance is the magnitude of PQ cross L over the magnitude of L. So now the magnitude is the square root of the sum of the squares of the terms. This is the square root of 64 plus 49 plus 1 over the magnitude of L, which is the square root of 1 plus 1 plus 1. Well, it's really 1 squared plus negative 1 squared plus 1 squared. So at the end of the day, this is square root of 114 over the square root of 3. So again, this is a fairly complex problem. There's a lot to be done in it, so take a while to digest it. Just to review, I'm going to draw all over the page, so you can pause and look at it for a while before I mark everything up. But keep in mind what happened here. We were given the symmetric equation of a line right there. I needed to know, really, the first goal is to get these two things, is to get a point on the line and to get the direction. Now, I did it by rewriting it as the parametric equations. There are other ways to do this. You could try and rewrite the symmetric equation in a more familiar way. You have options, but the key is to get an L and a P. I need an L and a P because that's what comes into this formula right there. I need 3 things for that. I need L and P for the line, and I need Q, which is not on the line. Those are the 3 critical things. So my first step down here was to get the P and the L. Then I knew the Q because that was given right there. And so then I found PQ because the formula says I need PQ. And then I found PQ cross L because the formula says so. And then I just used the formula to get the final answer and simplified it a little bit just to get a number looking thing. So that's the end of 11.5. Equations of lines in 3-dimensional space. 11.6 is on equations of planes, which are actually a bit easier. And like I said before, I'm not drawing a lot of lines, right? We're not drawing a lot of these things because they're hard to draw. And in fact, drawing them isn't one of our priorities. Working with them is one of our priorities. Drawing them, not so much. So that's the end of 11.5.